All right, so let's have a look at this problem 4 that gave me such problems. It is a calculus problem, and I could solve it using related rates because I am given a rate that well, I'm actually not given a rate. That's what makes this problem so tough, is that, in fact, I'm amazed that it's here. This problem has no business being here. First of all, it is a calculus problem, and it's a difficult calculus problem. It's more difficult than almost any related rate problem we dealt with last year. And oops, you've been around, or you still there?
Yeah.
Okay. I hear a beep every now and then. It makes me think I lost audio. Have you been hearing me the whole time?
Yeah, I've been hearing you. My mic, it says like my connection might not be good enough
Okay.
to
Okay.
talk sometimes.
No, I don't think I missed anything you said. Um, in other words, they give us, in a typical related rate problem, they would tell you what the rate that the water was being pumped in at. They would give you a number. And then they would say, tell me what the height of the water is as a function of time when time is 3 seconds. In other words, they would give you all these numbers, and that would allow you to solve for the one related rate, which is dH dt, the rate that the tank is filling as a function of time. So I could do that, and then this graph that they're looking at over here, let me do this. The answers are these three graphs over here. And the reason I pulled it up is because that's the best way to explain it, is to show you the answers. The best way to answer this without calculus, and you can do it, it just takes a little bit of thinking about it. Let's say that I had two containers. One was shaped like that. The other had the same top, only it was a rectangle. Like that. Okay? This is an aquarium. This is a cone-shaped something. If I pour a gallon of water into each one, which one is going to be higher? That one or that one? Yes, because there's such a tiny width at the very bottom that when you pour water in, it goes up immediately. And in fact, the higher up I go, if I pour another gallon of water in, it won't go this same distance up. It'll go just a little bit less because it's getting wider and wider. So another gallon would make it do that. Another gallon would make it do that. Whereas with the fish tank on the right, the first gallon, if it makes it do that, the second gallon's going to make it do that, the third gallon's going to make it do that, so forth and so on. So this curve, the height would start out high and go flatten out. Whereas this curve would be a straight line. It's a constant height that's going up linearly with time. Now let's look at the two shapes that we're given here. Three shapes. Notice that as I fill this, I'm starting down there, right? Where the width is small. The width of the part that I'm filling with water, let's start in the middle. It's a little easier to understand the middle. If I pour a gallon in, it goes to there. If I pour another gallon in, it goes to there. If I pour another gallon in, it goes to there until I fill it up. So that's why that would be the graph of B. As you pour water in, the height goes up linearly, depending on how much you pour in. Okay? But notice what happens with A. That doesn't happen with A. The very first gallon I pour in might get to there. And then as I go up towards the middle, when I get to there, that is the slowest possible rate where the height is going up. In fact, these lines get closer and closer together, and then it goes up really slow, and then as it gets near the top, it's going to fill up really faster again. There's going to be separation as I get to this area where the width decreases. And so this fits perfectly. It starts out, the height going up relatively quickly, but then it flattens out as it gets to the middle of the cylinder. And then as it gets to the top of the cylinder, it speeds back up. And finally, shape number C, you have the really wide part at the bottom. So the first bit of water makes the height go up, but not very fast. But as you get closer to the top, it goes up faster and faster. Oops, I should be widening these things like that. And so with C, the height goes up slowly, 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 but then as I get near that top, it's going up a lot faster. And so this problem number 4 can be analyzed completely visually, graphically, and understanding what would happen if you actually poured water into these things. You don't need to do calculus. If we did, I would have to make up numbers for all of it. And then I would have to draw an elaborate graph based on a bunch of different numbers. It would be much harder than any related rate problem we ever did in calculus. Nonetheless, it could be done, and you would end up seeing that the first function would look like that, the next one would look like that, and the third one would look like that. If you solved it mathematically and did all the work, it would just take a lot longer. It'd be harder to do. All right. Let me do this. Let me minimize the answers. Let's maximize the problem sheet. Blow it up a little bit and continue on. Now we did number 5. We did number 6. Didn't do number 7 yet. So we need the basic equation that relates things that are directly proportional or inversely proportional. Always try to start any problem, especially a new problem. This is different than the previous couple. It's actually similar to 6. 6 was something was either directly proportional, jointly proportional, or inversely proportional. Well, this is the same kind of problem. Notice the wording. For certain category hurricanes, the cube of the diameter of the hurricane is roughly proportional to the square of the hurricane's duration. So how can I write that?
D squared, T squared.
Hold on. Let's go left to right. The cube of the diameter. That's how you write that.
D cubed.
Is proportional.
So times T squared.
I need a K. Always got to have a K. Don't forget the...
So be K times T squared.
Square of the time. Okay. So that's what that equation says. That equation says that the diameter of the hurricane cubed is proportional to some constant that we don't know yet times the duration, the square of the duration of the hurricane. Write an equation to represent the relationship solve your equation for d. Well, if d cubed equals this, what does d equal?
The cubed root of k/t squared.
Okay. And this k changes for every model. In other words, the previous problem had to do with the speed of the airplane and the area of the wings. That was a different k. That's a k that applied to that airplane only, not even all airplanes. Probably in general all airplanes, but specifically to that airplane, you could figure out what k was. And if they gave us enough information, we can figure out what k here is. And they're going to in problem B. So let's solve for k. Let's put in everything we know and hope that the only thing we're left with is k. And then we can solve for it. Got our equation, now fill it in.
So 302 equals the cubed root of k times 273
Squared. 273 squared. Whoops, hold on. This is enough to calculate k.
Yeah.
Once we've calculated k, then we will have a specific equation for hurricanes. And this equation does kind of apply to all hurricanes, especially since they said roughly proportional. Okay? That means this equation probably does work for almost every hurricane, no matter where it's at on the Earth. The diameter of the hurricane is roughly proportional, or the cube of the diameter is proportional to the duration of the hurricane. So you could figure out how long a hurricane is going to last if you knew its diameter. And this was actually pretty significant during these two recent horrible hurricanes that hit Puerto Rico and Florida. They knew the diameter. They could tell what the diameter was from outer space. They could measure it. So they had a real good way of estimating the duration of the hurricane. And it wasn't pretty because the diameter was about the biggest diameter they had ever seen for a hurricane coming out of the Atlantic. So do you have your calculator in front of you?
1 second.
Okay.
Yeah, I got it.
The first thing I'm going to do to solve this for k.
Cube both sides.
All right. What's 302 cubed?
A really big number. 27543.
I'm sorry. What? I'm sorry. Start again.
275 43608.
Okay. What's the right side?
It's just k times 273 squared.
Go ahead and square 273.
$74,529.
529
Yep.
times k. So k is equal to what? The number on the left divided by the coefficient of k, correct?
Yep.
And you're going to have to come up with it because we can't do the rest of this problem without knowing what k is.
369.569.
369, can we round off 0.569, so 370. And there's a reason I'm rounding off to a whole number. It said it was roughly proportional. So there's no point in making K accurate to 3 decimal places. You know why? I mean, it's roughly proportional. So we're really going to round it off. I'm rounding it off to the nearest integer, 370. Now, what is our equation? When I say now, I don't mean the general equation. What is the specific equation for hurricanes? D is equal to what?
The cube root of 370 times t squared.
Yeah. And now we can answer every question they might ask about hurricanes. All hurricanes. But not tornadoes, not snowstorms, just hurricanes. So they want to know what the diameter would be if the duration was 140. How am I going to solve that? I mean, if you need an answer, do you have to fill these out, or is this just for your education purposes?
This one's just for my education.
All right, we don't need you to do this on the calculator. Just tell me what to fill in. What's the diameter of the hurricane going to be?
The cube root 370 times 140 squared.
Correct. Whatever that number is. It's going to be greater than or less than 302 miles? Without doing the math.
Less than?
Yeah. In other words, bigger diameters go with bigger durations. And this duration is only 140 hours. That's about half of the previous one. So I can't say the diameter is half, but I do know that it's smaller. And it's not half, because one is the cube and the other is the square. So it's not a one linear relationship. All right. What are they asking here?
If the two are like related.
If it's a function. No, there's a very specific definition of function. What is it? It's got to pass the vertical line test. Okay? If I draw these data points, and that's week 1 through 6, and at week 1, I got a data point that's at 3250. Week 2, it's at 3,500. Week 3, it's at 3,450. Week 4, it's at 3,700. Week 5, it's back at 3,500 again. And finally, at week 6, it's 3,800. Is that a function?
Yeah.
Yeah.
No vertical lines.
Exactly. In other words, if I want to see if a bunch of data points are a function, the easy way to do it is go ahead and connect them and see if it passes the vertical line test. And it does. No matter where I pass a vertical line, I only get one value of y, the account balance. What would make it not be a function is if I had multiple week 2s. In other words, if they had said week 2 it's 3250 and at week 2 it's 3500, that means when I get to week 2, I got 2 points right above themselves. That's not a function right there. That fails the vertical line test. So that's all they're asking is it a function of week? Yeah, and you don't have to, they didn't ask you whether it was a linear function or whether it was a quadratic function. They just said, is it a function? Yes, it is. We don't know exactly. It looks clearly that it can go up or down. So your account balance is probably like a stock market portfolio. It may go up some weeks, it may go down others, but for any given week, it has a certain value. Therefore, yes, it is a function of week. All right, number 9. I need to scroll down and get some writing space here. What's the first thing we need here? And in case you're not looking, in case you're not recognizing that thing they're asking for, notice that is the definition of derivative. The limit of that thing as h goes to 0. That's what it is. Remember back to the tortuous days where you had to solve derivatives by doing it the hard way?
Yeah.
This was the hard way. So this is kind of a calculus question without being a calculus question. They don't tell you find the first derivative. They just say, do this and simplify. So it's going to have all the difficulties of a hard algebra problem. But what's the first thing we have to do? We know what P of t is. What's the other thing we have to figure out?
H.
No, we got to figure out P of t of plus h. That's what we need. That's what we got to plug in right there. Is P of t plus h. We know what P of t is. They gave it to us. What does P of t plus h equal to?
It's just 5 over t plus 1 plus h.
Well, let's do it in the right order. Substitute for t, t plus h, and then plus 1. Yes. Okay. So now, here's what we have. 5 over, I can remove those parentheses, I don't really need them, minus, well, 5 over t plus 1, that's P of t, and the whole thing's going to be divided by h. Now, what's my next step towards simplification? Whenever you have a fraction in the numerator, especially if you have two fractions, solve the numerator first. Forget the h in the denominator for the moment. How do I perform this operation? How do I take this fraction and subtract that fraction?
Make an like in the same denominator.
A least common denominator. What down here below, or over here on the left, I'm going to do it. You still there?
Yeah.
I'm going to write really small. That's just the numerator I'm dealing with here. What is my least common denominator?
T squared plus h plus 1.
Don't multiply it out. Leave it in factored form.
T plus h plus 1 times t plus 1.
And you'll see why it's better to leave it that way. What's the numerator got to be?
Just 5 minus 5. Or
5 times t plus 1. Here's the reason you leave it in factored form. Because I can now look at that and realize that it's exactly the same as that. And that's what's important. It has to be exactly the same. Otherwise, I've made a mistake. Had I multiplied the bottoms together, I wouldn't be able to tell. The math would be too tough. I'd have to factor it again. But as long as I leave it in factored form, I can instantly see that this t plus 1 cancels with this t plus 1 and leaves me with what I started with. So now let's do the same thing with the second fraction. Common denominator is still this. What's this numerator?
5 times.
What's got to go into parentheses so that this fraction is the same as what I started with?
T plus H plus 1.
Perfect.
I don't know. I lost like connection or something there. I don't know.
Okay. And when you know what happened when you lost that connection? I lost my drawing tablet.
Ah.
Yeah, my cursor has disappeared. Huh. Interesting. I wonder what happened. It's too coincidental that both of those happened at the same time. Let me plug that in and see if that solves it. Maybe. Oh dear. That's terrible. What goes in the parentheses?
T plus H plus 1.
Okay. Write that somewhere, will you? So I don't have to redo this from the start. When I'm going to have to close this out, reopen it, and rewrite this. This thing on the bottom, write it. So you can read it back to me when I do this. Got it?
Okay, I got it. Yep.
And let's see if I can do it simply by doing this. No. Well, what are my other options here? Reopening this document from the get-go. Nothing. A mouse. A mouse won't write on it either. I think I'm going to have to take my ultimate solution. You know what that is?
What's that?
Reboot.
Ah.
The only way I can get this to work. And
Okay.
I don't see being able to. I'll reboot and text you a new meeting ID number within 3 minutes.
Okay.
Okay? Talk to you in a bit.